As you can tell by the lack of videos on ideal gas laws, there's really not a lot to talk about. It's the ideal gas law. Now, told you in the previous video, ideal gas, pressure times volume, PV equals N RT. That's really the gist of the ideal gas law. There is one consequence of the ideal gas law, though, that you do need to be familiar with, and this is what's called Dalton's law. Now, there are several iterations of Dalton's law, so let's try to go through a few of them. The basis of Dalton's law is that if you look at an ideal gas, every molecule has the same kinetic energy. And because of that, each gas molecule, regardless of what it is, contributes equally to the pressure exerted by the gas on the container it's in. This tells us then that the pressure due to the individual gas is proportional to the number of atoms or moles of that individual gas. So we use a term called partial pressure. And what partial pressure refers to is the pressure exerted on the walls of a container due to a specific gas. Now, because ideal gases expand to fill whatever container they're in, there's no such thing as a partial volume or a partial temperature. R and T are true of the container that the gas is in, as is the volume. The only thing we can dial in here are pressure and moles. So what are some consequences of this idea? Well, first of all, let's introduce an idea called the mole fraction for X. The mole fraction is the moles of the individual species you're looking for, I, divided by the total moles of gas in the gas phase. So if you have a mole of nitrogen and 4 moles of hydrogen, there's a total of 5 moles of gas. And so the mole fraction of nitrogen is just 1 over that 5, or 0.20. Now what Dalton's law tells us is that, 1, pressure due to species I is just the volume equaling the moles of species I times R times T. So this is just kind of a statement of the obvious. The pressure is going to be proportional to the number of moles, and this RT over V is going to be our scaling constant. Another consequence, which is a bit more useful, is that PT, the total pressure due to all the moles of the gas, times the mole fraction of species I is equal to the partial pressure of species I. So if we've already solved for the total pressure and we know the mole fraction, all we've got to do is multiply the two of these together, and this will give us the partial pressure of species I. Another consequence is that the total pressure is just the sum of the individual pressures. So if we know all the individual pressures, we just add them up to get the total pressure. We don't have to go through and solve the ideal gas law once again. The other thing we can do, though, which is kind of helpful when we start looking at trying to subtract out pressures due to components, is that if we have something like water vapor and air, and we want to know just the pressure due to the air, if we know the water vapor pressure, we can subtract that off the total pressure, and that'll give us the pressure of both nitrogen and oxygen air. So really, these are your 3 big consequences of Dalton's law. Individual pressure is going to look just like it does for the total pressure in terms of the ideal gas law. If we already have the total pressure, we just have to multiply by the mole fraction. This will give us the partial pressure. Or if we want to know the pressure of an individual species and we know the pressures of all the others and the total pressure, it's just a matter of subtracting off the components we don't care about.